Hey, hi, this is Kunal, and today I'm going to discuss about uh, performance metrics that will be useful for building AI ML model. So, why we need a model evaluation? We will discuss on that, and what are the performance metrics we need for a classification problem, and what are the performance metrics we need for regression problem. So let's go through the importance of model evaluation. So basically, evaluation of the model is crucial for assessing the performance of the classical classification or regression algorithm, and it helps us in understanding how well the model is making predictions and identifying the area of improvement. And it also helps us to understand which model works better, what is the accuracy, and what could if we talk about the just regressions classification problem. So some of the metrics are called accuracy, persistence, recall, f1 score, roc, under area curve. So these are the metrics we we try to see. And for if we talk about the regression model, then mean absolute error, mean square error, root mean square error, r square, adjusted r square, that help us to understand the uh, uh, about the accuracy of the model or how the model is performing, whether the model is overfit, underfit. So this help us to understand more into the more into performance of the model, and evaluation of the model help us to, I mean, it is have a directly impact on the business decisions, resource allocations, and risk management. Some model may be biased or something, that we can also check it out. So okay, so what are the metrics we have for classification or problem or classifications algorithm? So first one is called as a accuracy, and other is called confusion matrix. We use confusion matrix to drive other performance metrics called precision, recalls, F1 score. Other is a ROC, under area curve, and we have a log loss. So let's go into details one by one. So confusion matrix is a performance measurement for the machine learning classification problem, where the output can be two or more classes. And basically, it's a tabular representation of the model predictions against the actual value. We categorize them into the true positive, true negative, false positive, and false negative. And it also serves a foundation for various performance metrics called accuracy, precision, recall, F1 score, and it give a very holistic view of the model predictive capabilities. For a sensible model, the principal diagonal, we can say that this is the principal diagonal should be high, and the up diagonal FP and FN, it should be low. And for multi-class classification problem, the C class level should be C by C matrix. So let's understand what is the meaning of is a TP, FP, FN, and TL. So if we talk about this is horizontals level, that is the actual level we say, and vertical level is called predicted value. So on horizontal side it's a actual value, and the vertical side it is predicted value. So it is a positive, and this is for negative, and this is for predicted value as a positive, and this is for negative. So true positive means the value was positive and it has predicted true, and true negative means the value was negative and it has predicted as a negative. And FP means it's a false positive. It has predicted positive, but that is false. And FN means false negative. The model has predicted as a negative, but that is false. So instead of negative, it should be true. And here, instead of false, it should be instead of positive, it should be false. So this is how we can uh, take the reference of a confusion matrix. Okay. So let's go through the accuracy. Basically, how we are going to measure the accuracy. If we are going to measure the accuracy, it should be true positive plus false positive divided by true positive, false negative, and true negative. So that will give us the accuracy. So it is a simple ratio between the number of correctly classified points to the total number of points. So it should be, I think, true positive, and true negative. Divided by true positive, false negative, and true negative. So we have a limitation with the accuracy for classification problem. Okay. So if there is a, we have a very highly imbalanced data, say like that, if the mail is a spam or not, or ham or a spam. So here, most of the emails will be not as spam, and only a few of the mails is going to be a spam. So here, if you see that, if you take the reference of this example, we will have always a high imbalance data. Other examples we can take as for if a particular customer who is taking the loan will default or not. So most of the customer is going to have a non-default. Only a few of the customer is going to be resulted into the default or defaulted. So here also we have a, I mean, very imbalanced data between the defaulted and and non-defaulted. So this is called imbalanced data. And if that is the case, so suppose we have a 95% of the value as a non-defaulted, only 5% value is a defaulted. So in that scenario, the model will try to predict that the customer is non-defaulted. So here our model is biased, will be a biased, and it will always try to predict that are non-defaulted. Understanding the context of a classification problem is essential for interpreting the accuracy, as it may not accurately represent the model effectiveness in scenario with a disparate class distribution. So we have to understand the context of the problem, and according to that, either we have to go for precision or recall, or we have to go for F1 score where we. So that is the reason we need an understanding of the business context. Other like in a state of accuracy, we can go for precision, recall, and F1 score based on the business, a kind of business uh, we have, and we are building a model for it. So first comes as a precision. So precision tell how many correctly predicted class actually turn out to be positive. So usually in the cases where false positive is higher concerns than a false negative. And if we talk about this scenario, suppose we are having a loan application. Here we asking the model to predict whether the person is going to be defaulted or non-defaulted. And if basically it's try to it is I mean, we take this scenario where we have a false positive as a higher concern. So if a person which is going to be non-defaulted, and model is predicting he's going to be default, in that scenario it is a business loss, and as well as it is the right person who is not getting the advantage of the loan. So in that scenario, we are concerns about the persistence. Persistence will means we have a higher concerns on the false positive. Other is a recall, we call as a sensitivity as well. So it tell means basically, if we talk about the persistence, it tells about how useful the results are. Basically, I mean, what is the accuracy we can achieve it. Uh, I mean, how many true cases it has predicted and how many it hasn't. Uh, it has predicted the wrong. And for if we call about this recalls, so basically how many of the actual positive cases we are able to predict correctly with our model. So it tells us about how complete our results are, and we go for recaller sensitivity when we are more concerned about the false negative. False negative means if we say that uh, if we talk about the medical field or healthcare field, we do not want a valid patients to mark as a false. Like some people is got infected like a COVID, and if we try to predict as a not COVID, then it is going to be a serious concerns for us. For similar cases, we go for the recall or sensitivity. And how to call the recall? It's a true positive, a variable true positive, false negative. It is a F1 score. So it's give a combined idea about how precision and recalls matrix, and it is a basically a harmonic mean of precision and recalls. We use it uh, when false positive and false negative both are equally costly, and true negative is high. And it is try to balance between the precisions and the recalls. Other is like ROC, area under the curve. I think it should be AUC. Okay. So ROC is a probability curve that plot the true positive rate against the false positive rate at various threshold value and separate the signal from the noise. Basically, ROC curve is generated by plotting the cumulative probability function of true positive along the x-axis and false positive rate uh, into the y-axis. And ROC area under curve is a single value matrix used for evaluating the model performance. Higher the AOC, better the performance. And 0.5, the value of 0.5 suggests that there is no description between, and a value between 0.5 to 0.7 is considered as a good, and anything beyond 0.7 is a good to go model. We use when our data set is unbalanced, and it's mostly used for comparing the different models. Other is called log loss or logistic loss or cross entropy loss. So it is one of the major metrics to assess the performance of classification problem, where the predictions of a probability value comes between 0 and 1. Lower the log loss, better the predictions of the models. So far we have learned about the performance matrix that is useful for classification problem. Let's try to understand what are the performance matrix we need for regression problem. So regression problem is where we try to predict a continuous dependent variable using a set of independent variable. Uh, if we just give some example like weather forecasting, share marketing, house pricing, etc. Prediction error is be called as a residual, and it is basically a difference between the predicted value and actual value. And the regression model basically try to produce the smallest difference between, try to fit a model with the smallest difference between the actual and predicted values. If residual are 0, the model predicts perfectly, and if where the residual is not 0, it means that model is it is having some biasness. So let's go through some of the model performance metrics for regression problem. So first one is called mean absolute error. It is nothing but an average of the absolute differences between the actual value and the predicted value. A small ME suggests that the model is great at the prediction. For large ME, there is some issue with the certain area into the model building, and it is robust to the outliers. Other, we have a mean square error. It is the average of square differences between the actual and the predicted values. Similar is a lower the value, better the regression model. It is not robust to the outlier. Third, I mean, we mostly use root mean square error for evaluating the regression model. Called We take the average square root difference between the real value and the predicted value, and it is also we can also say that it is the square root of mean square error, and lower the RMS value is better the model with predictions. A higher RMS indicate that there is a large deviation between the predicted and actual value. Max error is nothing but max error between the actual and the predicted values. Other metrics are be used, are called R square. R square basically measure the proportion of the variance of dependent variable with respect to the independent variable. It is one of the popular metric for identify the model accuracy, and basically it is good if we have a single features. If we have a multiple feature, then it's not work perfectly because it will always try to increase the R square value whether that feature is significance or not. So that may not give the that will not give the the correct value, because it will always try to increase the value and for some irrelevant feature as well, which is not correct. To solve this problem, you go for adjusted R square. And how to calculate the R square is nothing but it is the ratio between the SSE and TSE. SSE is nothing but sum of a square of residual, and TSSE is nothing but it's a total sum of a square between the actual value and the mean of actual value. So let's go with the adjusted R square. So it is same as a standard R square, except that it penalizes the model with additional feature are added, which is insignificance. So adjusted R square generally penalize adding more independent variables to not increase the explanatory power of the regression model. The value of adjusted R square is always less than the value of R square, which is range between 0 to 1. So basically any model which is above the 0.8 be considered as a good model. And that's the references we have. So that's all for today's discussion. Thanks for watching. If you like my video, please like, share, and subscribe.